All right, why don't we go ahead and get started. Today, for our seminar, we have Shahram Abbassi, who's alias Shahram. He's an associate professor at Purdue University.
Yeah.
And also a researcher at IPM, the Institute for Research in Fundamental Sciences. Previously, they just started the Institute for Physics and Mathematics. It's changed the name and kept the acronym. And yeah, we're going to be talking today about reaches.
Yeah, thank you so much for inviting me and giving me this chance. I am almost theoretical astrophysicist. I'm going to talk about black hole accretion disk and some new issue that need to be addressed. I put almost a long introduction for the people that they are maybe not familiar with this field. I'm talking about accretion as energy sources, low luminous AGNs. Then I will talk about ADAFs as a well-known model to describe AGN activities. I will talk about the pros and cons of ADAFs, and then I will try to introduce inflow outflow solution and some of our recent papers. As you maybe know, quasars is very remarkably luminous objects that they change their luminosity in very short time scales. The energy of this object is comparable with the entire galaxy in a very short, since they are very young, and if you want to describe this huge amount of energy, we need a strong and enough energy sources. Certainly, nuclear energy cannot describe energy produced by AGNs, since if we want to have such huge amount of energy, we need to burn 10 power 8 solar mass hydrogen to helium to produce such big and huge amount of energy. It's almost impossible because the length scale of quasars is just a few light days, and it's almost impossible to have such amount of solar mass hydrogen instead of this small length scale. On the other hand, the hydrogen timescales, hydrogen burning timescale is quite high, and it's not be reliable to have such events in the quasars. Seems gravitational energy would be a good resources for producing this huge amount of energy. Consider a neutron stars with one solar mass and the size of 10 kilometers. If a mass goes from infinity to the surface of the neutron stars, release 10 power 16 joules per kilogram energies. It's quite comparable with the releasing energy through the hydrogen burning. If 1 kilogram hydrogen released is 0.7, rest mass will convert to energy. While if accrete from infinity to the neutron stars, normally 20 times greater than energy will be released. 6 cross 10 power 14 joules per kilograms. Now consider that if the central mass becomes very massive and the radius be very small, the amount of energy will release is very huge. And seems the accretion process is the most important process that can reproduce high energy luminosities. Accretion powered object, we have several kind of accretion powered object, young stellar object, cataclysmic variables, X-ray binary, ultraluminous sources, and also active galactic nuclei. I'm going to talk about these systems, active galactic nuclei. Normally their properties is the luminosity is 10 power 12 to 10 power 13 luminosity of the sun. The spectra is nanostellar. Time variability is almost short, and some other relativistic effects like these jets. This is a nice picture captured by a Hubble Space Telescope. If we zoom inside this of active galactic nuclei, you will see a very, very hot media. It's this media is normally believed that is ADAF, advection-dominated accretion flow regimes. Now, why black hole accretion disk interesting? Because of several reasons. Black hole is very weird and mysterious object. Many kind of accretion black hole in the universe have been observed, and different observational manifestation comes from the black hole: radiation, jets, winds, and many things else. For black hole accretion disk, at first, standard thin disk model was proposed and introduced by Shahram in 1976. The physics of Shahram disk is the disk is cold, geometrically thin, optically thick, spectrum is almost black body, and radiative efficiency is high. This model was very successful to reproduce the spectrum of many accreting systems, even in cataclysmic variable, binary stars, or even protoplanetary disks. But hot accretion flow at first was pointed out by Ichimuro, 1977, and finally completely introduced by Narayan E. in 1994. The physics of hot accretion flow is geometrically thick. It's not comparable with this thin disk. Is remarkably hot, 10 power 12 Kelvin, optically thin, and high radial velocity. A spectrum is very complicated. It's not black body one. And radiative efficiency is very low. Since that time, several models have been proposed for the black hole accretion disks: Shahram disk, a slim disk, ADAF, and SLE. And the other one is luminous hot accretion flows. You may find all details in this review article, Yuan and Narayan. But what is the condition of ADAF? Actually, ADAF is present if in a two extreme, very slow accretion rate or even in very high accretion rate. In very slow accretion rate, the gas is unable to radiate its heat less than the accretion timescales. So the disk is radiatively inefficient. So the energy will store in the disk and advect to the accretion material to the central stars. On the other hand, when the accretion rate is very high, the radiation is trapped and unable to escape from the accretion flow. And in both of cases, we have advection-dominated accretion flow, and the disk is radiatively inefficient. But traditionally, a slow accretion limit is named as ADAF, and high accretion rate is a slim disk. You can see here in this picture. This part of the disk is very low accretion rate, and for high accretion rate, we have a slim disk. In 1997, Abramovich modeled a slim disk, and Ramesh Narayan model is now the best framework for the people that they are doing ADAFs. By the way, the equation of ADAF is quite complicated. I don't know. I can use pen. The main difference between the thin disk, Shahram disk, and ADAF is energy equation. Energy equation, we have Q plus minus Q minus. In the case of Shahram disk, Q plus equal to Q minus. And then we have Shahram disk. While if Q plus minus Q minus is F Q plus, when F is less than 1. This is ADAF. We mean some part of viscous energy generated in the disk will store in the disk and cannot radiate it away. F is the advection parameters. When the F is 1, equal to 1, we have in a fully advective regimes. This is a set of equation in the ADAF regimes. ADAF was successfully to reproduce many spectrum of many AGN systems by very complicated radiation mechanism. Bremsstrahlung from high energy electron, synchrotron emission, synchrotron self-compton emission, and so many people believe that it is a very good candidate to describe the physics of hot accretion flow. But
For the case of the synchrotron emission, where are the magnetic fields coming from? Are they also coming from the disk?
Yeah, come from the disk. I think so. I'm not expert in this field, but I know that people using solution from ADAF, they can reproduce you will see each of these terms comes from one of mechanism.
So what they assume of the magnetic field, the equations you showed in the previous slide only discussed the hydrodynamics, not the evolution of the magnetic field.
At first, the effect of magnetic field was not considered. Okay, I'm going to talk about the magnetic field effect. This is a fully hydrodynamic analysis. But on the other hand, we have low luminous AGNs. More than 40% of nearby galaxies contain low luminous AGNs. The luminosity is very low compared to Eddington luminosity, and the SED is non-black body and no broad iron line, K line, and double-peaked H line, and many manifestation. For example, our center of our galaxy, Sagittarius A, is a unique laboratory for low luminous accretion disk. It's very important for us because we have detailed spectrum and we have lots of detailed that be addressed by the models. Nowadays, ADAF is very well known and very well modeled to describe the physics of low luminous AGN. But what is the cons? Although ADAF works well for Sagittarius A and other low luminous objects, there have some details that need to be investigated. The most important thing is the dynamical role of magnetic field, since the fluid is very high, has very high temperature, and so the magnetic field probably play an important role in these systems. And on the other hand, compared to the Shakura-Saniev disk, the ADAF is remarkably thick, and using one-dimensional analysis is not so good, and we need to take care about the vertical structure or substructure of the disk. The modeling more sources is required to check and deepen in our understanding to accretion disk. These two cons, I'm going to talk about each of them. Non-magnetized and also HR. At first, when 1994, Ramesh Narayan introduced the first 1D solution for ADAF, he used average quantities for the vertical structures. Since the disk is remarkably thick, H over R is almost 1, he started to consider the vertical direction. In 1997, he solved another, he proved that assuming average quantities for the physical quantities is not so bad, and the result is very good agreement with the 1D solution. One of the main assumptions in the Narayan solution is that he assumed that the accretion rate is a constant with the radius. If we assume this assumption, we have a density profile like this, which means that this is the density index. But how about the simulation? Several simulations have been proposed and have been done. Stone-Pringle, Igumenchev, they tried to model hot accretion flow, but in almost all of them, they find that the accretion rate is not constant and increases with increasing the radius. It's not constant at all. We should be like this, but simulation shows that it goes up with going out from the central stars. Consequently, the density profile is steeper than that we assumed. And it's 0.8 almost, but Narayan solution shows that is 1.5.
So if it's, you're saying that the accretion rate
Yeah.
increases with the radius.
Yeah. When you are going outside, we have more accretion rate in the outer part of the disk.
So you lose it to winds.
Yeah. There are two scenarios. One scenario is producing and losing winds. The other scenario is the disk is convectively unstable, and convection will change the accretion rate smoothly. In 2000, Narayan and Abramovich introduced another solution, convection-dominated accretion flow, which described such kind of systems, and the system is convectively unstable. But the other solution is the inflow-outflow solution.
I don't understand the convection. Convection doesn't eliminate mass. Convection only moves mass from one point to another point in the disk. So how does it solve it? Because you have conservation of mass.
Yeah.
If everything stays in the disk, you can't accumulate more mass there. So how does convection solve it?
I don't know exactly, but even some simulation shows the convectively unstable systems, and also they find some reliable solution for convectively. I guess that the convection is in the vertical structure, change the picture. I don't know exactly, but I need to read it. But I'm trying to talk about this model. This scenario is introduced first by Blandford-Begelman in 1999. They introduced inflow-outflow solution. Meanwhile, some simulation like this shows convectively unstable system, and many people believe that convection will answer this issue. But solution presented by Begelman-Blandford, inflow-outflow solution, will be the best solution. Actually, ADAF at first was introduced by Narayan. He mentioned that the Bernoulli function in the ADAF solution is positive. So seems the connection between outflow wind was obvious. It's because the Bernoulli function of the flow is positive, and potentially the disk can have such kind of behavior. Nowadays, we believe that some other simulation shows that inflow-outflow solution is a better solution. You will see the behavior of the flow near the surface is almost going to outflow. Here it is inflow and outflow. Let's talk about the observational evidences of outflow. Yeah, there are several indirect observational evidences for the producing outflow in these systems. All of them, they are indirect, is not direct. Because detecting the wind from the hot accretion flow is very difficult compared to the Shakura-Saniev disk. But in 2013, for the first time, this Chinese group could confirm the outflow from our central AGNs. But in physical point of view, there are several mechanisms to producing outflow. We have thermally driven outflow, magnetically driven outflow, or radiatively driven outflow. But why outflow is important? In one hand, the outflow is very important because if we consider outflow in our solution, the ingredient of accretion physics you need to change many things in the structure of the disk. And also outflow will have a fingerprint in the observation, and we need to take care about the outflow. On the other hand, for the people that they are doing AGN feedback, studying outflow is very important. because outflow can bring a huge amount of mass and momentum to the galactic environment, and in somehow can suppress star formation on that. So for the people that they are doing AGN feedback, studying the outflows, energies, and estimating the mass is very important. Yeah, so this kind of solution can strongly affect galaxies formation. Radio mode is related to ADAF physics. By the way, after this long introduction, I'm going to talk about our experiences since last couple of years ago. We have several kind of solution in two branch. The first branch, we are trying to modify inflow outflow solution of Begelman-Blanford for a MHD case, adding the magnetic field effect. And the other part, we try to find exact solution for the vertical structure of ADAFs. The aim of this work is the vertical, restudying the vertical structure of the disk and the possible role of generic magnetic fields. Let us start with the first paper. Structure of ADAF with outflow, the role of toroidal magnetic field. The main concern that the solution presented by Narayan was not show any outflow solution, because just for some simplification, he assumed V theta equal to 0. If you want to have outflow, this is theta. For the flow to change the direction to outflow, we need to take care with the non-equal V theta equal non-equal 0. I mean that I don't know why. I guess just for simplification, Narayan assumed V theta equal to 0. So the solution is purely inflow solution, not outflow. If you take non-zero V theta, the equation becomes too complicated. And we try to do that at first. There are several solutions with non-zero V theta. The famous one is the Begelman-Blanford and the other people. In all these works, magnetic field is not included. On the other hand, magnetic Prandtl number in the hot accretion flow is almost 1. And we need to take care about magnetic resistivity in the disk. Simulation shows that this magnetic Prandtl number is quite high. So we take this equation. The novelty is that we add the magnetic field effect and also magnetic resistivity. And the other equation is the same. We used self-similar solution for the radial direction, and for theta direction, we use this boundary condition, and they are some of our solution.
The fact that resistivity doesn't this spoil some similarity? Because you introduce another scale.
We use the Prandtl number as a constant, so we use the mimic it as viscosity.
So it's like having a resistivity that changes with the radius.
Yeah, it's normal assumption in this field. Yeah, you will see that the resistivity in the equatorial plane cannot change the picture. This is the velocity. You will see that in somehow here, for example. V r equal to 0, then change the sign. From here we have inflow, the other part is outflow. But for the different amplitude of magnetic field, you will see that in somehow magnetic field enhanced the outflow. Stronger magnetic field enhanced by outflow, and the solution is comparable with the data comes from the simulation. Density index, this is the density index, 0.8 almost. And the other components. But we tried to a much more realistic model for magnetic field. For the magnetic field, two models have been proposed. One, odd symmetric configuration or even symmetric configuration. Odd symmetric configuration, the magnetic field is like this, while even symmetric is like this. Even symmetric configuration is more popular compared to the even one, compared to odd one. The even symmetric case has become fashionable, but the odd symmetric case we study may be more realistic because the odd symmetrics is related to dynamo process in the disk. And there are several papers that show that in the hot accretion flow is more reliable to assume even odd symmetric. But people in the simulation normally use the even symmetric. For the odd symmetric, we need such kind of boundary condition like this. What?
What is the
For, we are trying to odd symmetric. Here is much more better to show. Radial component of the magnetic field is like this, and B field like this. B theta should be 0. This is the boundary condition in odd symmetric configuration. And the magnetic field is field line is like this.
You use the assumption of equipartition.
Yeah. And for different input parameters like resistivity, density index, phi component of magnetic field, and the radial component of magnetic field, we try to study the effect of magnetic field in the structure of inflow, outflow. You will see that here. A strong BR like this will try to enhance outflow, while B phi, strong B phi, enhance also. But maybe this fix may show better than. Yeah. BR is quite difficult. I think the first picture has some error. By increasing BR, the radial component for the magnetic field, outflow structure will suppress. While for the B phi, it's vice versa. Stronger B phi will enhance producing outflow. And also for different values of magnetic resistivity. Stronger magnetic resistivity supports stronger outflow structure. And one interesting result in our paper is that this is the gas pressure, contour of gas pressure, and contour of the magnetic pressure. In somehow, the magnetic pressure becomes very strong near the poles. Maybe it's related to producing jets in the disk. At the same time, one of my colleagues, Feng Yuan in China, Shanghai Observatory, they solved the same problem with even symmetric configuration. We published both of papers at the same time. The result is like this, and they published the same time. Last year, I started to do something else. Asymmetric B field. I had a visit in Cornell University using Richard Lovelace's expertise. We tried to asymmetric configuration for the magnetic field. The motivation was that there are some observation from agents that they show one-side jets. I mean that the system has jets from one side and there is nothing on the other hand, on other side. We believe that the magnetic field can describe this behavior. So we use the same physics, but we use asymmetric configuration. This is odd symmetric boundary condition. This is even symmetric configuration. And for asymmetric, we have all three components. I mean that the magnetic field is not aligned, and there is three components.
What creates the symmetry? How does the the black hole decide if it should launch a jet in one direction or the other?
I don't know exactly, but in somehow seems this is the disk. If the magnetic field is not exactly aligned, then, for example, if you have BR, B theta, and B phi here, because if one of them becomes 0, you are in symmetric or even symmetric configuration, odd or even symmetric configuration. If you have 3 of them, which means that there is no asymmetric. We named it asymmetric configuration. The problem becomes more and more complicated to solve, and you will see that this is the results of odd symmetric configuration, and this is from asymmetric configuration. You will see that by changing something, input parameter of magnetic field, the structure and vertical thickness of the disk is also changed. You will thicker disk in the upper side and the thinner in the inner side. And they are asymmetric, even symmetric. We compare all of them. Let's try the same figure of our last paper. Also, we put some other restriction because we are following the subsonic solution. We put this restriction, Mach number less than 1. You will see that by changing the variable, you will have outflow from one side and nothing from other side. And for different values of parameter we have studied. It's quite complicated. We studied the structure of magnetic field outside and inside the disk, upper side and inner side of the disk for different configuration. I refer you to, if you want to read more, you can refer to our paper. Was published in M. Ross last year. This is the first part of my talk, and I'm going to the second part of the talk. Vertical structure of the disk, why is important? Actually, when Ramesh Narayan introduced his solution, he introduced radial self-similar solution for the radial direction and remained a set of differential equation. He solved it with 2-point boundary condition numerically. So the solution is not purely analytic. In these years, we tried to find a fully analytical solution for the vertical structure of the disk to know what happened inside the disk. The motivation is that that's paper, Wei Minggu in 2009. By comparing the advection cooling with viscous heating, they put a big question for ADAF. Because when F equal to 1, fully advective disk, the vertical thickness of the disk becomes P over 2, 90 degree, which means that the ADAF is not possible to be slim. It's quite thick for fully advective regimes. We try to recalculate his model by imposing magnetic field. At first, we start with just purely toroidal magnetic field. We add toroidal magnetic field in the equation, and we solved them exactly the same as Wei Minggu. We find some restriction for the rotation velocity of the disk, and also the temperature of the flue in the equator. Just want to show these pictures. This picture is the same as Wei Minggu 1 for F. You will see that for stronger magnetic field, the disk becomes thinner, and probably this adding magnetic field effect in the ADAF solution. This question will be resolved. I mean that the magnetic field keep the disk is slim. And in the second paper recently, we tested for poloidal magnetic field. we find the same solution for the poloidal magnetic field. It was published in AppJ 2007. But the other part of our solution, the motivation is that, let me say something else. Nowadays, simulation shows some substructure in the vertical structure of the disk. Some simulation shows that we have slim inflow regimes, we have outflow regimes like this, and in somehow we have disk jet here, or maybe corona and jet here. You will see the different substructure have been observed in the simulation, and their fingerprint is also observed in the simulation. But there is no any unique solution for each of these substructures. At first, we try with some of my colleagues and my students, we find exact analytical solution for ADAF for the vertical structure. The assumption was simple. The main difference between our solution and the Ramesh Narayan one is that where we just assumed one component of the tensor momentum, and we also assumed theta viscosity as a theta function, like this. They are our solution, and is very comparable with the solution presented by Ramesh Narayan. Since the time is left, I'm going to just our new results. Just last a few weeks was published in the AppJ. This is one of our most works. I'm talking about this. We used Fourier analysis to find these substructures. At first, just for test, we tried to refine and recalculate the Narayan solution using this assumption. We assume the equation quite similar to the Narayan. It's exactly the same. Narayan used alpha viscosity prescription. We used the same. Furthermore, we assumed another model for viscosity, which is depend to theta. And we adopt radially self-similar assumption for the component, the same boundary condition, but for the vertical component, vertical term, we used Fourier terms. We truncated, because of the limitation of our computer facilities, we just truncate for some terms, 6 or 7 terms for the each quantities. Just look at, amazing, because our solution is exactly the same as Narayan one with a different method. This is ours, this is Narayan one. We tested several times, and the solution is exactly the same. And furthermore, we used a new form for viscosity, theta dependency for viscosity, and we find very interesting results. It's very comparable with the Ramesh Narayan one. And yeah, this is solution with the latitude angle dependencies. You will see VR, V theta is for different values of advection parameters. By the way, to being sure that the result is true, we need to take care about convergence of the solution. You will see the result with 4 components, 5 components, and 6 components. After 6, the Fourier terms becomes converge, and the other terms becomes to 0. So we are sure that the result is converge and the solution is very good. At the next steps, we try to add non-zero V theta. the problems becomes very complicated. Our computer facility is not enough to calculate this strong term, because for finding this solution, we need to take 50 equation with 50 unknown. By guess, we need to take to choose one of these unknown quantities. It's quite difficult to achieve, but seems Fourier analysis is very powerful tools to recover the standard solution. In our point of view, we add some test dynamical stability of the solution. The result is quite interesting. But we believe that this kind of solution, Fourier analysis, because Fourier analysis is very friendly with the magnetic field. It's easy to add magnetic field effect, and also thermal conduction effect seems it's very important in such kind of the disk. In near future, we are trying to develop our codes for this substructure. Because inflow outflow solution is not powerful tools to find these substructures, since you need several boundary conditions each time, and boundary conditions is very sensitive to the physical quantities in the equator. So, I was in Harvard last year. Narayan is also looking for any exact solution that describes this such a structure. Normally, all of available solutions can describe inflow and outflow structure roughly, not exact, and cannot describe furthermore up to the pole, and the connection of the solution with jets. But seems Fourier analysis is powerful enough to detect and find this solution. Thank you for your attention.
So we have time for questions. Are there any more questions?
So if you don't describe the jet in the solution with the Fourier transform, what do you assume about the boundary conditions? So you have to assign some boundary condition.
Yeah. Actually, solution presented by Narayan Yi is a 2-point boundary condition. One condition in the equatorial plane, other on the pole. But our solution is one point boundary condition. We put extra physics in outside to be sure that the physics is still valid. For example, non-zero Wi-Fi and something like that. But it's impossible to impose the boundary condition outside.
I have a question. You're talking about magnetized accretion disks. We haven't mentioned MRI at all.
MRI is not active in the ADAFs. Normally, it's playing role in the standard disks, since the disk is very high temperature, low density, and yeah, so on. MRI is not important in the physics of ADAFs. And also, ADAF is the ADAF regimes is very close to the central black hole. Far from the black hole, this condition is not valid. So we have thin disk, very close to the disk. Since the main spectrum of the disks, AGNs, comes from very close to the black hole, the physics of black hole is very important. Physics of ADAF. But is roughly from 10 Schwarzschild radius to 1,000 Schwarzschild radius of each accreting black hole is ADAF. The outer part becomes thin and becomes a Shakura-Saniev disk. But since the main part of the spectrum comes from the inner side, the physics of ADAF is very important.
Well, if there are no further questions, let's keep reading.
Thank you.